All right, 11.3 is all about simplifying radicals. And as someone who also teaches college algebra, I can tell you that this section is very helpful. For a lot of students who go straight into college algebra and they haven't done radicals in a minute, this is one of those things that kind of pops up that they're like, oh, I don't remember how to do any of these. And in college algebra, we don't have the time or the space to go back really and review them. So this is actually a really nice section. So I've made a list of perfect squares and perfect cubes. These are a good reference. These are good ones to kind of have memorized. Obviously there's more, especially for the squares. Hopefully you can go higher than 4 squared. Hopefully you know 5 squared is 25, 6 squared is 36, and so on. I would say it's good to know perfect squares up through 12. 12 times 12 is 144. It just saves you a lot of time if you don't have to rely on your calculators. Same thing for perfect cubes. Perfect cubes, I would say probably up to 5. 5 cubed is 125. That's probably a good range. After that, I would say use your calculator and see what you can come up with in terms of finding those perfect cubes. Because today what we're going to end up doing is we're going to simplify our radicals, and they're not always perfect cubes and perfect squares and perfect quadruples or whatever. A lot of times we're going to have to break down our number or our expression into multiple different products that do have some perfect squares or do have some perfect cubes. And so if we can identify what these perfect squares or cubes are, it saves us a lot of work of trying to figure out what comes out. One safe way of working through any of these problems, though, is to do a factor tree on whatever it is that is underneath your radical. That is always a safe bet to go back to if you don't know what perfect square or perfect cube may live within a number or an expression. Another thing that's going to be important as we work through these is being able to break apart our variables into perfect squares and perfect cubes. So x squared, that's the same thing. I mean, this doesn't really change anything here. We have the x term being squared. But understanding that when we have x to the 4th, that's the same thing as saying x squared squared. That will help us when we go to simplify it. Or if we have x to the 6th, it's the same thing as x to the 3rd squared. The more we can break these down and set them up as something squared when we're doing square roots or something cubed when we're doing cube roots, it will help us when it comes to actually then applying that radical to that expression or that number. So these tables are kind of just nice reference points, kind of get your brain thinking about perfect squares, get your brain thinking about perfect cubes. But we are able to use a calculator as well to help us find some of those. So don't be afraid of using your calculator. But I also don't want you to rely on a calculator too much. So nice list. And then today we're going to have 2 different rules that's going to help us to break apart our radicals and simplify our radicals. So the first one is at the very bottom of the screen right now, and it's called the product rule. And basically what it states is you can take the nth root of a product. So a times b, if that's underneath the radical, we can split that into 2 separate radicals. We can split that into the nth root of a times the nth root of b. What's nice about this is if we have a number or an expression underneath the radical to start with that isn't a perfect square or isn't a perfect whatever our nth index is, we can split it so that we do have some stuff that does simplify out. You will be doing this in college algebra when it comes to your quadratic formula, and you have to simplify it out as far as you can. And it's one that causes students to miss quite a few points because they'll stop too soon. They'll think, oh, this is completely simplified and we're good to go, when in reality there's still a perfect square hidden in there that we can take out. So the product rule we're going to use, and then we'll learn the quotient rule after we do a handful of examples using the product rule first. You ready to try some? All right. I noticed in my handwritten notes that I had mislabeled. Like I have A, B, C, D, and then I skipped E for some reason. Don't know why. So they will be labeled correctly here. But just know that once we get to E, that's F in the handwritten notes, and so on and so forth. Same problems, just they're mislabeled in my handwritten notes. Okay. So remember, if you have a radical and there's no index on it, then it's understood that that index is 2 and we're taking the square root. Now, if you type the square root of 32 into your calculator, it is not a perfect square. It's not. So what we need to do is we need to think about what times what gives us 32 that may be a perfect square. And we can think back or even look back up at our list of some perfect squares where 4 is a perfect square or 16 is a perfect square and things like that to try and help us identify these. But again, if you have no idea what times what gives you 32, then you're going to have to do some kind of a factor tree over to the side to find out what times what will give you 32. I cannot stress enough knowing your multiplication and division tables. I know that sounds crazy to mention in a college classroom, but if you've used a calculator for most of your academic career to do these, then you're setting yourself up for a really hard time in your next math classes. And so this is a spring class. Take the summer. Really get those in rote memory to where you're like, okay, 32, that's 4 times 8, or 16 times 2, or whatever. That you can really come up with these factors pretty quickly without having to use a calculator or a factor tree. Okay, who wants to tell me a factor of 32? Do what? What times what gives me 32? 16 times 2. That one will give me 32. And that's actually the nicest one we could come up with. So, remembering our product rule here, we can have the square root of 16 times the square root of 2. The reason why this is nice is 16 is a perfect square. When you square root 16, you're going to get 4. Square root of 2 is not a perfect square. Your homework problems today will tell you to leave things in simplified radical form. They are not going to want decimals. They want you to simplify it out as far as you can. And so the way that you know you're done is ask yourself, is there anything under the radical that I can pull out? 2 is not a perfect square, so there's not. On this one, I'm going to kind of flip down, and I'm going to show you, actually I can do this. I'll pull it up over here. I'm going to work it one more time, because maybe you don't realize that 32 is 16 times 2. A more common response would be 4 times what? 8. So that's more likely what you would immediately go to. Well, the square root of 4 is 2, but the square root of 8, that's not a perfect square. But 8 is 4 times 2. Square root of 4 is 2. 2 times 2 would give you 4. So you can do it this way where you do multiple steps and you keep simplifying, and again, until you get to the point where you say, is there anything under the radical that I can pull out? And there's not in this case. Same answer. We had different factors, but we still get there in the end. Questions? Okay. Let's look at B. Square root of 60. What times what gives me 60? Do what? 30 times 2? Is that what you said? Okay, so 30 times 2, but neither of those are perfect squares. That's okay. So let's see, let's do a little factor tree. We've got 2 times 30. Remember how factor trees work? 2's prime, so we're done with that branch. What times what gives me 30? 10 times 3? Okay, 3's prime, so we're done there. And what times what gives me 10? 5 times 2. Yeah, 5 times 2. Okay, so we've done a factor tree now for 60. So how does this help us to determine what is going to be coming out of this radical. Well, do we have any branches that are the same? The 2's, yeah, because remember the ending is what we would say is our prime factorization of this number. 60 is 2 times 3 times 2 times 5. So when you have multiple branches that are the same, that means those are squared. Because if I did the prime factorization of 60, I would say it's 2 squared times 3 times 5. Right? Well, if I wrote that with radicals, because all this is under a radical, I'd have radical 2 squared times radical 3 times 5 is 15. When you square root a square, they go away. Or you could say that that's 4 under there, and the square root of 4 is 2. 15 is not a perfect square. 3 and 5 are not perfect squares. So 2 radical 15 is as simplified as we can get with this one. So if you do a factor tree, what you're looking for is what duplicates. Do I have anything that shows up more than once? Write out your prime factorization like this, and then stick it back under radicals. If you notice that it was 60 and 60 is 4 times 15, then you could have done that at the beginning, which is what I did in my handwritten notes. But again, it all really depends on what do you see. What factors do you actually see? And so, like I showed you with the radical 32, there are multiple ways to get to the same answer. Questions or clarifications on these first two before we try something with a different index? Okay, let's look at a cube root. We don't play with cubes that often. So cube root of 54, I'm needing to look at cubes. So I did give you a short list of the top 4 cubes. You know, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. Now, if we're taking the cube root of 54, I know it's not going to be here. I'm not going to use anything from 4 greater because 64 is greater than 54. So I need to ask myself, is 54 divisible by 8? Because if it is, then I will be able to do something with that. So on my calculator, I take 54 divided by 8, and I get a decimal. So it's not divisible by 8. So let's do 54 divided by 27. All I'm doing is I'm testing these perfect cubes to see if any of them come out. And when you take 54 divided by 27, you get 2. 54 is 27 times 2. So I can split this using my product rule into the third root of 27 times the third root of 2. The third root of 27 is 3. So when you have no idea what it's going to do, because like third roots are a little bit weird, and our next problem is fourth roots, that's kind of how we're going to approach it. We're going to start with our lowest cubes and see if any of them divide out. Can we get to a number that's playable, that works? All right, let's look at a fourth root. I didn't give you a list of fourth roots, or fourths. 1 is really boring. I'll go ahead and tell you that, because 1 to any power is itself. So next to this problem, I'm going to figure out what 2 to the 4th power is, just for a reference point. On your calculator, depending on which one you have, if you ever need to do like higher powers, you can type in the base, so 2, and then this caret button right here, it's called a caret. That's putting it up there in the exponents, and then whatever your exponent is. So 2 to the 4th is 16. And if you wanted to, you could even do 3 to the 4th just to see where that lives. 3 to the 4th is 81. That's really big. There's no way I'm going to have 81 times something to give me 96. Not going to happen. So odds are 96 is divisible by 16. That's really what I'm looking for. 96 divisible by 16 is 6. So the fourth root of 16 times the fourth root of 6 equals 96. Now, we just found that 2 to the fourth is 16. So the fourth root of 16 is 2. And that's all you can do. You do that for any of your indexes. If you have something like the fifth root of something, the sixth root of something, start with 2 and 3. See what those raised to those indexes are, just to kind of give you a starting point or a reference of maybe what's going to go into that number or the expression underneath. Questions or comments before we throw in variables? All right, 11.2, that's what we did last time. What did we do with our radicals? Like, what was the whole point of 11.2? Who remembers? Yeah, we went back and forth in 11.2 between radical form and exponential form. And with our exponents, we went to fractional exponents. And I will tell you, when you have variables under your radicals, a lot of times going to that other format is going to be way easier. Way easier. So if you remember from 11.2, the way that this works, I'll flip this over so we can have a little notes section right here, is if you have the square root of x, that's the same thing as saying x to the 1/2. The index outside became the denominator of our fractional exponent. The power in here becomes the power on top. Converting over to this and then simplifying this fractional exponent a lot of times is a lot easier than splitting apart into using our product rule. So let's look at E. E says the square root of x to the 16th. Now, you can work this using the product rule, but it's a lot simpler to use our fractional exponents. So, fractional exponents, the power inside stays on top, and then the index out here becomes our denominator. So, I have x to the 16 over 2 power. Well, what's 16 divided by 2? 8. This is x to the 8th power. Done. Really what you end up doing is you take the exponents divided by whatever that index is. That's all we're doing. And that simplifies. And sometimes it'll simplify all the way out, and sometimes it won't. These first ones are going to simplify all the way out. When we get to h, it's not going to simplify all the way, but we can still use the same process. Or we can use a combination of the processes, I guess. So y to the 27th, we're taking the cube root of that. If we write it in exponential form, that's 27 over 3. Well, 27 divided by 3 is 9. G says the fourth root of z to the 16th. What's that going to simplify to? Z to the 4th. Because we'll have z to the 16 divided by 4, which is z to the 4th. Now, h is different. 9 is not divisible by 2. But what happens if I pull one of those x's off? What if I make this into a product of x to the 8th and x? I just took one of my x's off. That way I would have something divisible by 2. Because x to the 8th times x is x to the 9th. This goes back to chapter 5. I think it's 5.1. Well, this would be x to the 8 over 2 times radical x. 8 divided by 2 is x to the 4th. And we still have that radical x because that one's not going to simplify. It's not a perfect square. We can't take it out. So sometimes you just have to ask yourself, how do I get my exponent to be something that's divisible by my index? Remember, the index is the little number outside. That makes sense? Let's look at I. I is the 5th root of x to the 23rd. 23 is not divisible by 5. What number is divisible by 5 that's near 23? 20. Yeah, it's like the Price is Right. You want to be under the number they give you. So x to the 20th, I could take the 5th root of that, and that would leave me with the 5th root of what over here that you can't see? X to the 3rd, yeah. Because remember your product rule of exponents, if the bases are the same and you multiply them together, you're adding those exponents. So this would be x to the 20 over 5 times the 5th root of x to the 3rd, x to the 4th, 5th root, x to the 3rd. If you're dealing with only exponents and variables underneath your radicals, a good way to check if you're done simplifying is if the exponent underneath your radical is less than your index, you're good. But if your exponent, let's say this said x to the 6th, the 5th root of x to the 6th, we wouldn't be done yet. We could still pull out a whole other x to the 5th. So this needs to be less than the index out here, or we're not done. All right, let's do one with a couple of variables at play. It's L in my handwritten, it's J on here. We have the square root of x to the 12th, y to the 17th. So immediately I would use my product rule that we're talking about today to split these. I would split it into x to the 12th times the square root of y to the 17th, and then really I'd approach it like two separate problems. I'm looking at the square root of x to the 12th, and I'm looking at the square root of y to the 17th. 12 is divisible by 2, so I can play with this one as it is, because I can do x to the 12 divided by 2, which is x to the 6th. 17 is not divisible by 2, so I'm going to take one of those y's off, so that I have y to the 16th times radical y. I'm just doing my product rule again, is what ends up happening here. Y to the 16th divided by 2 radical y. 16 divided by 2 is 8. So split them, and then you can work them really as separate problems, because everything's being multiplied together. Most of your problems, let me look, so I did your homework. Most of your problems deal with regular square roots. You have 4 problems that deal with cubes and 1 problem that deals with a 4th on your homework. This next one is dealing with a 4th. So I'm still going to choose to split it because I have x to the 6th and y to the 23rd. I'm going to use that product rule to split up my variables. 6 is not divisible by 4. But what number is divisible by 4 that's less than 6? 4. So I can split this. The 4th root of x to the 4, which leaves me with the 4th root of x to the what? 2. Yeah, because 4 plus 2 will get me back up to 6. So I've just split this. And I can do the same process over here for the 4th root of y to the 20th. And then that will leave me with the 4th root of y to the 3rd. There you go. 4th root of x to the 4th will just give me x. 4th root of y to the 20th, that'll give me y to the 20th divided by 4. 20 divided by 4 is y to the 5th. Now, we don't like to leave it like this. This is gross. There's lots of radicals. It's all spread out. So we can combine this back together. Same way we split it using the product rule, we can go the opposite direction and bring it back together because they're both being fourth rooted and it's all being multiplied together. So this is going to simplify completely into x, y to the fifth, fourth root of x squared, y to the third. You want to end up with just one radical in the end. You can have multiple things under that radical, but you want to have one single radical at the end. On Pearson, they give you lots of options to do different types of radicals. It just takes a minute to get used to the buttons. Questions, comments, or clarifications on any of these product rule problems? How we did them, how we split them, what we're looking for, all that jazz. All right, I told you there's 2 rules today. This was the first one. This was product rule. The opposite of product is quotient. So we have a quotient rule that lets us split up a single radical into multiple radicals, or combining multiple radicals into a single radical. If you have the nth root of a divided by b, that's the same thing as taking the nth root of a divided by the nth root of b. Obviously, b cannot be 0. We can never divide by 0. Why is this helpful? Sometimes it's going to be helpful to have one big fraction underneath your radical. That way you can simplify first before applying that radical. Other times it's going to be simpler to split and look at your numerator separate from your denominator and simplify those outside of each other. It just depends. You may prefer one way or the other. That's totally okay. I'm actually going to show you how it works both ways on A, how you can use it where they stay separate radicals, or you can combine it, and it's really your preference, or whichever one kind of jumps out at you first is really what's going to end up happening. If you see it one way, go that way. Or even if you start heading down one route and it's not really working out well for you, try it the other way. If you try using a single fraction first and it's really getting complicated, try splitting it up and just looking at the top and bottom first separately and then see what comes of it. So for A, I will work 2 different ways. The first way, I'm going to keep it separate. I'm not going to apply my quotient rule. I'll keep it as we're going to look at the top and we're going to look at the bottom separately. So then we have to start with what times what gives me 63? And there's more than one answer, but really what I'm looking for is, here's the deal. I have radical 7 on the bottom, so can I multiply 7 by something to get me 63? 9. 7 times 9 is 63. So one way to approach this problem is to use my product rule, that's what we did first, to split radical 63 into radical 7 times radical 9. Whoops, that's a 7. So I've kept my radicals separate, the numerator and the denominator, and now I have a radical 7 over a radical 7. Those can be canceled, meaning I just have radical 9. Well, what is radical 9? 3. So this one I didn't use the quotient rule. I kept everything separate. Stuff canceled. It was nice. Totally fine. Now, it won't always work that way. And you don't want to leave radicals in your denominator. That's something you always want to try to avoid if you can. So let's see what happens with the quotient rule. If I would have applied the quotient rule to this, I would have had one big radical with 63 over 7 like this underneath. And then I would have either known my multiplication tables and known that 63 divided by 7 is 9, or I would have typed 63 divided by 7 into my calculator and found out it was 9. And again, I still get to 3. It's really a preference, or it's what you see first. When it comes to dealing with numbers and exponents in the mix, a lot of times it will be easier for us to do this big fraction with the radical on the outside so that we can simplify it on the inside first. That's what we're going to do with B. B, we have the third root of 128 xy to the fourth over the third root of 2xy. Just looking at the denominator, I can't take the third root of 2xy. None of those are perfect cubes. So right there would be a good indicator that I need to apply my quotient rule and look at this all as one big fraction. So I bet you stuff's going to simplify, and I'm going to have a perfect cube in here somewhere. First thing I notice is that 128's even, so it's divisible by 2. So that 2 on the bottom is going to go away. 128 divided by 2 is 64. So I canceled those, simplified them out. Now I'm going to look at my x's. Notice I have an x on top and an x on bottom. Well, those are going to go away. And I have a y to the fourth on top over y. What's that going to leave me with? Y to the third. So now I have the third root of 64y to the third. Well, that's the third root of 64 times the third root of y to the third. What's the third root of 64? 4. And the third root of y to the third is y. So all of this yuck goes all the way down to 4y. But looking at it in the beginning, if I would have kept it separate, I couldn't have gone anywhere. So the quotient rule is nice for combining and then simplifying. Questions, comments, clarifications? Okay, C is another one where it's all numerical. We have a big radical of 121 over 25. You could work this one either way. 121 is not divisible by 25, so there's not really a lot I could do there. But I could just take the square root straight out of the gate of that if I recognize these are perfect squares. If not, I would probably go ahead and opt to use my quotient rule and do my square roots separately. Because I know the square root of 25 is 5. But maybe I don't recognize 121 as a perfect square. But 121 is. It's 11. Either way, you're going to get to 11/5, whether you split it or you do it all at the beginning. All right, let's look at D. D, we have one big radical. We have the third root of 8x to the fourth y over 27xy to the 10th. 8 and 27 have nothing in common. But I could simplify my x's and y's before I do my quotient. And that would be helpful. So my 8 and 27 are kind of stuck. But notice I have an x to the fourth over an x. Those will simplify, leaving me an x to the third on top. I have a y on top and a y to the 10th on bottom. Those will simplify to where I have a y to the 9th on bottom. At this point, I would choose to use my quotient rule to split them and look at them separately. Again, personal preference. But once you split them, you can use your product rules to split them further and simplify. The third root of 8x to the third, that's the same thing as the third root of 8 times the third root of x to the third, which is 2x. on the bottom, the third root of 27, y to the ninth is the same thing as the third root of 27 times the third root of y to the ninth. 27, the third root of that is 3. Remember, third root of y to the ninth is the same thing as saying 9 divided by 3, so it'd be y to the third. You'll probably get to a place where you don't feel like you need to use the product rule to split this, and that's totally fine. You do as much or as little as you need so that when you go back, you know what you've done. Because if you accidentally drop a number or you invert a number and you get it wrong, you want to be able to go back and look at your work and make sure you understand what went wrong and where it went wrong. All right, let's do one more. Do 1 to the 4th. We have the 4th root of 18x y to the 5th over 3x to the 9th y. Again, this is set up as one big radical to get started with, so I'm going to choose to go ahead and simplify anything and everything inside there that I can first. 18 divided by 3, that's 6, so I can put a 6 on top. Then I look at my x's. I have an x on top and an x to the 9th on bottom. That will leave me with x to the 8th on bottom. Then I look at my y's. I have y to the 5th on top over y. That'll leave me with y to the 4th on top. At this point, I would choose to split. So I'd have the 4th root of 6y to the 4th over the 4th root of x to the 8th. The top, I would choose to further split using my product rule. 4th root of 6 times the 4th root of y to the 4th. And then on the bottom, I don't really have to do anything. I could write it as x to the 8 divided by 4 if I wanted to have an additional step there. But x to the 8th divided by 4 is x squared. The 4th root of y to the 4th is y. And if you type in the 4th root of 6, you're going to see that that doesn't work. 6 is not a perfect 4th, as we would put it, so it's going to stay underneath that radical. And either you can write it like this, where you have the radical living up there on the top, or you can write it where the yx squared is the coefficient to the 4th root of 6. These are the exact same answer, and they're totally fine. If you stick the 4th root of 6 down there in the denominator, then you've changed your answer, and then it does not work. One thing I would discourage you from doing is I would discourage you from putting like the 4th root of 6y over x squared. This is the same thing as the top one, but you're more likely to accidentally stick that y under your radical by putting that y term second. So anything you've taken out of your radical, I would always stick in front of the radical. Rearrange things, move it around so that it lives out front, just so you're not accidentally sticking it back under that radical and getting it wrong. Because that's frustrating and annoying when